Okay, so hello everyone, it's 6 o'clock. Still people may be joining, so I'll wait for another 4 or 5 minutes and then start with the session. Okay, thank you. Okay, thank you all for joining in today's session. Let's start with the proceedings then. So, hello everyone, I am Somnath Hazra and this is week 6 of the CS100 NPTEL live session on operating system fundamentals. So, in this week we will be studying a few questions related to scheduling and synchronization. We had looked into a few problems related to scheduling in the previous week, week 5. So we'll be continuing with a few more and a few questions related to synchronization. So thank you all for joining. Let's start with the questions. So this is the first question. Which scheduling algorithm do you think is non-preemptive? Like it cannot be preemptive even if you want to design it in that way. round robin scheduling, shortest job first, priority scheduling, or first come first serve scheduling. So which among the following do you think is non-preemptive by design? Like if you want to make it preemptive, the name does not stay the same. It does not stay the same. It becomes something else. So which one do you think is the answer? So what happens in round robin scheduling, as you may know, that each process is given a certain time quantum, and after that time quantum is exhausted for that process, so the next process is given the chance to execute in the CPU. Okay, I got one answer, that is shortest job first. Any other answers? So what happens in shortest job first is, so this is the ideal scheduling process where what happens is that the shortest job that is currently there among the processes in the ready queue, so that is executed first. So this is the optimal scheduling algorithm, and it is not practically possible because the operating system does not know from before that which process will execute for how much time in the CPU. But there are estimations for the same. So based on previous history, there are certain estimated times that can be used for scheduling. So I got another answer, first come first serve. Okay, so yeah, as I was saying, there can be estimations of the time that can be taken for the current process based on the times that it had taken previously. So that can be a good estimate for implementing an algorithm that can be close to SGF. In priority scheduling, as the name suggests, that there are certain priorities associated with the processes, and the higher priority processes, they are allowed to execute in the CPU before the lower priority processes. But what happens in first come first serve scheduling is that since we have a ready queue, and among that and from that queue, the process that has first appeared in the queue is picked up for execution, and if that process is preempted in between, then it does not it no longer stays as first come first served, because the process that has currently been picked up, that is the process that executes first, that has first arrived in the queue, right? So that should be the process that gets to execute in the CPU first. But if the process that is executing in the CPU, it is preempted to give to some other process, to give the CPU to some other process, what happens in that case is it no longer stays as first come first served, right? Because the process that came after it in the ready queue, so that process is currently scheduled then. So by design it stays as non-preemptive, the first come first serve scheduling algorithm. So that is the answer. Okay, so let's move on to the next question. So shortest job first algorithm can be preemptive only, non-preemptive only, either preemptive or non-preemptive, or none of the above. So which one do you think is the answer, right answer for shortest job first? Anyone would like to contribute? Okay, I got one answer. Anyone else would like to contribute? Okay. So as I was describing, the shortest job first algorithm is the ideal algorithm, and it gives the optimal usage of the CPU that can exist. So all the processes, the waiting for all the processes, the waiting times are the least that can be possible. Okay. So what happens in preemptive shortest job first scheduling is that the currently executing processes, if it has a time quantum, if it suppose for example the CPU process that is currently the process that is currently executing in the CPU, it requires 4 units of mode, 4 milliseconds more to execute in the CPU to complete its process. But another process that appears in the ready queue requires 3 milliseconds to complete in total. It has been picked up by the long-term scheduler and put up in the ready queue recently. So what happens is that the currently executing process, which will take 4 more milliseconds, will be then preempted, and the new process that has arrived, which will take 3 milliseconds, that will be given the CPU, and that will continue executing. So this is another variation, the process that I just described. As you may know, this is another variation of the shortest job first, which we call as shortest remaining time first, because the process that was previously executing in the CPU, we are taking into account the time that is remaining to be executed in the CPU. So that is 4 milliseconds was remaining for the process that was there already in the CPU. So the new process that is being picked up, it has 3 milliseconds to execute all in total. So since its remaining time is shorter, so according to that, the new process will be old process will be preempted, and new process will be given the CPU time. So there can be non-preemptive versions also. Yes, there can be non-preemptive versions of the same also, as you can understand, where the process that is currently executing in the CPU, that cannot be preempted, even if there is a shorter process in the ready queue that has newly arrived. So once it executes once it completes its execution, then only the newer process can be given the CPU time. So as I said, there can be both variations. So both preemptive and non-preemptive variations exist of the shortest job first algorithm. Let's go on to the next question then. So which is optimal but most difficult to implement? Round robin scheduling, shortest job first come first serve scheduling, none of the above. So which among the following is the most difficult to implement? I already answered this question. Yes, shortest job first. Anyone else would like to contribute? Yeah, so yes, so yeah, shortest job first is ideal, is optimal, but it is very difficult to implement because what the primary criteria of shortest job first algorithm is that it requires the running times of the processes that are present in the ready queue, but that is very difficult to measure, to tell a priori. So what happens practically is that there are various estimates, as you may have studied in the course, regarding the running time of the processes based on its previous history. So according to that, the running time is estimated, and an algorithm that is somewhat close to shortest job first is implemented in practical scenario. Okay, so it is very difficult to obtain the ideal running time. So somewhat of an estimation is done. Okay. So next, let's go on to a numerical related to scheduling. So 6 processes arrive in order, that is P1, P2, P3, P4, P5 and P6. So this is the order of the queue. So calculate the average waiting time using first come first serve, given the following details. So the processes are given, the corresponding burst times are given as signified here for each of the processes. So now you have to calculate the average waiting time. So I'll give some more time here since this is a numerical problem. So yeah, please, if anybody comes up with the solution, you may contribute in the chat box. So it is a comparatively simple numerical, since the order is exactly same as the ones in the table, that is P1, P2, P3, P4, P5 and P6. Okay, I got one answer, 25.5. Anyone else? .83. Yes. Anyone else would like to contribute? So we have to calculate the average waiting time. Okay, the average waiting time. And since this is FCFS, so no question of preemption or anything like that. And this is the order that in which the processes appear, and these are the burst times. Okay, let's move on to the solution then. So as I said, since P1 is the first in the ready queue, so it does not have to wait, it immediately gets the CPU time. Next is P2, so it comes only after P1 has completed its execution, that is 9. So all these times are in milliseconds. Okay, so consider the standard as milliseconds. So, yeah. So this is that comes up to 9. So after that comes P3. So it has to wait for both P1 and P2 to complete. So its waiting time is 9 plus 1. Actually, the sum of these two. So then comes P4. It has to wait for all these three. So 9 plus 1 plus 14. Similarly, you do it for up to P6. Okay. And then you will get the waiting times for all the processes, like this one is 9, this is 10, this comes up to 24, then 26, and then it is 32. Yeah, and then you have to do an average of all these, and then you will get the average waiting time as 16.83. So yeah, 16.83 is the correct answer, as you can see. Okay, let's move on to the next question. So that was using FCFS. Now the question turns to using SJF. So using shortest job first, what happens is that, so now the question still is the same, that you have to calculate the average waiting time, but the algorithm is different now, that is using shortest job first, and there is no question of preemption or things like that. So once a process is scheduled, it moves up till completion, it continues up till completion. So as I said, this is the optimal process, this is the optimal algorithm for scheduling. So yeah, let's see what is the difference in waiting time then. So according to shortest job first, it will pick up the job that is shortest, that is P2, because all these processes, although there is an order in the queue, but we have considered that all these processes have come together in the ready queue. So at current time 0, P2 is already there, which is the shortest job. So P2 is scheduled first, then P4. So then P4 has to wait simply for P2. Then comes P5. So P5 has to wait for P2 and P4. similarly you have to schedule the rest of the processes, and accordingly you get the waiting times for all the processes, and you calculate the average, and that comes out to be 10.5. okay, so from 16.83 the optimal waiting time, average waiting time that we can get is 10.5. okay, using shortest job first. okay, right. So but the problem is that the burst times for the processes will not be known a priori, so that we can before scheduling the process, okay, before the process has completed execution, it is practically not possible to know that how much time it will be spending in the CPU. So that is the problem. okay, anyway, let's move on to the next question then. So what is the correct order of completion using FCFS and using RR2? So by RR2 I mean round robin scheduling using time quantum of 2 milliseconds. So these are the details of 3 processes that are given. The burst times are given, correspondingly the arrival times are also given. So what is the correct order of completion of the processes? Can you say? So it will be better if you draw it with a Gantt chart. So for FCFS it should be pretty simple. So since there will be no context switch. So once the process is given the CPU, it will complete up till execution, up till completion. It will execute up till completion, and then the next process will come into picture in the CPU. So what will be the order of completion using FCFS? Can anyone say? At first we are calculating using FCFS. Would anybody like to contribute? It's pretty simple, right? So the arrival times are given. Okay, I got one answer. Anyone else would like to contribute? So at 0 milliseconds, at the 0th millisecond, only one process is there, P1, in the ready queue. Okay. At the 2nd millisecond, okay. At the 2nd millisecond, P2 arrives in the ready queue, and at the 3rd millisecond, P3 arrives in the ready queue. At the 3rd millisecond, P3 arrives. Let's move on to the answers then. I got 2. So for FCFS, I was saying it is pretty simple. So P1 is first scheduled, since it is the only process in the ready queue currently at the 0th millisecond. So P1 completes its execution up till 5. So by that time P2 has already arrived in the ready queue, followed by P3, because it arrives at 2 and then this arrives at 3rd millisecond. So P2 is now in the ready queue. It moves on up till completion. So 5 plus 7, that comes up to 12, and then P3. So that takes 3 milliseconds to complete. So that moves up till 15. So it is pretty simple. So P1 completes its execution first, then P2, then P3. Now when we move on to round robin scheduling, what happens? So the picture at first is the same, that is P1 is the only process in the ready queue currently. So it gets 2 units of execution at first. Now after completion of 2 units of execution, the ready queue consists of process P2, okay, because it arrives at 2 milliseconds. So since P2 is available, the CPU so the context is switched to P2, and then P1 is placed in the ready queue. So at this point of time in the ready queue, P1 is there and P2 is executing in the CPU, right? So this moves up till 4 seconds, 4 milliseconds. After 4th milliseconds, so at 4th millisecond, what is the picture? P2 is executing, and in the ready queue P1 was there, and in the 3rd millisecond P3 has arrived. So since after the 4 milliseconds has been expended, so after that the first process that is there in the ready queue, so round robin actually does scheduling in FCFS order innately. Okay, so if there are multiple processes, it will calculate in the first come first serve order. It will give the CPU in the first come first serve order, as you may know. So then P1 then comes next in the picture. So now in the ready queue, P3 is there followed by P2. Okay, so then P1 comes executes up till 6 milliseconds. So now P1 has completed 2 plus 2 4 milliseconds of burst time, CPU burst time. It only requires one more. So then P3 executes up till 2 milliseconds. So it also requires one more. So P2 then comes into the picture, since that was the process that is placed next in the ready queue. So when P3 is executing, P2 is there in the ready queue, and then followed by P1. Okay, so there is a context switch here, and P3 is given the CPU, and P1 is placed in the ready queue after P2. Okay, so what happens now? Yes, you have a doubt. That is RR selects the first element from the queue. Yes, it selects the first element from the queue that has arrived first. Yes, so that is what I was saying. So here what happens is that at the 2nd millisecond interval, P2 is given the CPU, and there is a context switch, and P1 is placed in the ready queue. Okay, so P1 is already there in the ready queue. P2 is executing, P2 is running. At the 3rd millisecond, P3 has arrived, P2 is running, and P3 is placed after P1. So after P2 has completed its 2 millisecond time quantum, P1 is the process that is placed at the top of the queue. So then P1 gets to continue its execution for 2 milliseconds more, not P3. Okay, so similar things happen for the rest of the time intervals also. Then P3 comes into the picture. So as P1 was followed by P3, so here what happens is that the queue picture is P3 then followed by P2. Okay, so then P3 comes into the picture. After that P2 comes into the picture. Then again this same thing happens. The queue sequence actually stays the same, that is P1, then P3, then P2. Keep that in mind. So after the 11th millisecond, P1 has actually completed its execution, because it has completed 2 plus 2 plus 5 milliseconds. So that is what it requires. So P1 is the process that completes first. Then P3 only required one more time interval, 1 millisecond more of CPU time. So that is what it takes here. So then P3 completes its execution. Then as round robin does a context switch after the time quantum of 2 has expanded, expanded. So there is a so it again looks at the ready queue, but there are no other processes that are present in the ready queue. So P2 continues executing up till 15. So P2 is the last process that completes execution. So the sequence here in case of round robin scheduling with a time quantum of 2 milliseconds is P1, then P3, and then P2. Okay, I hope it is clear to everybody. Is there any doubt? Okay. Okay, let's move on to the next question then. So yeah, there are 6 processes in the ready queue P1 to P6. Calculate the average waiting time using priority scheduling, given the following details. So the burst times are given and the priorities are given. So now you have to calculate the average waiting time. So I'll wait for a couple of seconds since this is again a numerical problem. So one interesting factor that you may have noted is that SJF is also a kind of priority scheduling, where the priority is implicitly present in the running times. So yeah, how much CPU time it requires, that determines the priority of the process internally, right? So SJF is also a kind of priority scheduling. Yeah, so that is just for information. Anyway, let's get back to the numerical. So I'll wait for a couple of minutes for you to complete the question. So if you have any doubts or anything, you can use the chat box now while solving if anything comes up. Okay, so what happens is here is that there are priorities associated with the processes and there are burst times that are associated with the processes. So what happens here is the higher priority processes are given the CPU time first, followed by the lower priority processes. So P6 gets to execute first, and then P5, and then P1, followed by P3, and after that P2, and then P4. Okay, so yeah, that I may have forgot to mention, that is higher the number, that is lower the number, more is its priority. Anyone would like to contribute to the answer? So you have to calculate the average waiting time. So yeah, let's go to the answer then. So yeah, as I said, the first process to execute in the CPU will be P6, since it has priority 1, so its waiting time is 0. Then next P5 will come. So since this is a non-preemptive type of priority scheduling, so P6 will complete its execution of 6 milliseconds, and then P5 will come to the picture. So its waiting time is 6 milliseconds then. that is of P5, then followed by P1. So its waiting, so its priority is 3 and waiting time is consequently 6 and 1. So P5 and P6 burst time. So those are the ones that needs to be considered. So similarly, then after that we need to calculate for P3, that is 20 plus 1 plus 6. So those are the times that you need to consider. So yeah, these are the individual waiting times, and if you calculate the average, it comes out to be 18.5. Okay, so this is the average waiting time for the processes. Okay, yeah, so let's move on to the next question then. If you have any doubt, please use the chat box. So it's better not to switch on the microphone, so it can create a commotion. Okay, yeah, let's move on to the next question then. So here we have just 3 processes, P1, P2 and P3. So each process, it is given that it first spends 20% of its time of the burst time doing IO, then 70% doing computation, and the rest of the 10% doing IO again, in that order. Okay, so the operating system uses the shortest remaining compute time first scheduling algorithm. So this is actually a variation of the SRTF, shortest remaining time first scheduling algorithm, where it only considers the compute time, not the IO times. Okay, so it does not consider the time of the IO while picking up the processes from the ready queue, and it is non-preemptive. That is, once a process is given the CPU time, it completes up till continues up till completion in the CPU. Okay, and another information is that IO operations can overlap. So there can be overlap in the IO sequence of operations. So what is the completion order of the processes then? So the burst times that are given are the entire span of the burst time over the process, over the lifetime of the process. So it includes the IO time, the CPU time, and then the IO time. So we have to mention what is the completion order of the processes. So I'll give a few minutes time. So considering this is a difficult problem, comparatively difficult problem. So your first step would be to calculate the individual IO times, the computation times, and the second IO times. Then you will get a clearer picture. Although the burst times are quite indicative of that, given the fact that it is constant and shortest remaining time first, it is just a comparative, it just becomes a comparative measure that which time is greater and which time is smaller. So this is constant across all the 3 processes. So the burst times always should be an indicative, quite a good indicative measure. But if you want to get a clearer picture, you have to calculate the individual CPU times and then move ahead. So no need to get confused with the long name that I have used here, that is shortest remaining compute time first. So you can think it as shortest job first. Okay. So since this is a non-preemptive process, so the remaining compute time does not matter. It is the job first, shortest job first, and since again, as I said, so you just need to compare between all the 3 processes. So yeah, the compute time also should not bother you too much. So it is just the shortest job first. So you just need to tell me what is the order of completion of the processes. Would anybody like to contribute? Yeah, that is what I said, that it is not actually SRTF. So Sonu is asking that SRTF is preemptive, but here it is mentioned that it is non-preemptive. So I am not actually using the SRTF algorithm. You can so it is, you can think it as shortest job first algorithm. And yeah, by name it is it may be preemptive, but you can use the same name for non-preemptive processes also. In that case, the remaining time is the burst time, is the CPU burst time. Okay. That is the information that you can use. Yeah. Okay, let's move on to the first step then. So the important information is that it spends 20% doing IO, 70% computation, and 10% doing IO again. So the burst times will come in this sequence. So the first 2 seconds of P1 it will spend doing IO, then the rest of the 7 seconds it will spend doing CPU burst in CPU, and then the rest of the 1 milliseconds it will spend again doing IO. Okay, so similarly things happen for the rest of the processes also. So what happens is that, so these are all the processes that are there in the ready queue. So yeah, it is better to use the chat box than to use the microphone, because it can create a commotion. If you have doubt, can use. Anyway, so what happens is that since we are using the shortest job first, which one among the 3 is the shortest? So P1 is the shortest, right? Considering the CPU burst. Even if you don't consider the CPU burst, if you consider the burst time also, P1 is the shortest. Okay. So since I have explicitly mentioned that you need to consider the CPU burst, so I am calculating the CPU burst. So so accordingly P1 will be the process that will be scheduled first. Okay. Actually, did I mention non-preemptive? Okay. So yeah, anyway, P1 will be spending 7 units of time in the CPU, then 1 unit of time it will be spending using IO, doing IO, input output. Okay. So in these 7 units of time, P1 cannot be removed from the CPU, right? So by that time, by this 9 microseconds time that has been spent on P1, P2 could have been yeah. So in fact, by the first unit of time, when P1 was first picked up from the ready queue into the running process into the CPU, so it will go directly into the ready queue, like it cannot execute directly, since it requires IO, input output operations first. So then the scheduler, the short term scheduler, will be looking forward to the next process that is that is currently there, next shortest process that is currently there in the ready queue, which is P2. Okay, so it will try to schedule P2, but P2 also requires IO, so P2 will also be removed from the running state. Okay, if you consider the process state diagram, then it will try to pick up the next shortest process that is there in the ready queue, which is P3, but P3 also requires IO at the current moment, so that will also be removed from the running state. So the shortest job first does not have any more processes in the ready queue, and it has to wait for 2 milliseconds in that similar situation until P1 is replaced in the ready queue, and it is the only process that can execute, that is there to be executed, left to be executed. So it has to be given the CPU. So by chance it is also the process that requires the shortest CPU burst, but even if it required longer CPU burst, that would be the only process that is left in the CPU, in the ready queue to be executed. So that is the only process that can be executed currently, right? P1. So P1 will be given the CPU, and that by the time the next process has to be picked up, 9 units of time, 9 microseconds of time have already been spent, right? So after 9 milliseconds, after 9 milliseconds, P2 is also there in the ready queue, P3 is also there in the ready queue. So which among these two do you think is shorter? P2. P2 has shorter CPU burst, so that process will be picked up next. Okay, it will continue for 14 milliseconds in the same way. Okay, then after that P3 will be picked up. Okay, so this is the complete picture of the Gantt chart, as you may know. So in the first 2 milliseconds nothing happens, nothing is there in the CPU. After that P1 comes into the picture. So after this time unit has been spent, so P1 comes into the picture. So in this time P1 is also doing IO, P2 is also doing IO, P3 is also doing IO. All three processes are doing IO in this unit of time. Okay, now after 2 milliseconds P1 comes into the picture, and it will continue execution for up till 9 milliseconds, because up till 9 milliseconds it will continue execution in the CPU. So in these 9 milliseconds what has happened is that, so from 0 up till 4 milliseconds P2 has completed its IO. From 0 up till 6 milliseconds P3 has completed its IO burst. So after 6 milliseconds P2 is there in the ready queue, followed by P3. Okay, but P1 is already running, and since it is a non-preemptive process, P1 will continue running up till completion. After P1 has completed, P1 will transition to IO up till 10 milliseconds, right? So in this time P1 will be doing IO, P3 is in the ready queue, and P2 is picked up from the ready queue, since it is the next shorter process that requires shorter CPU burst, comparing 14 and 21, right? So P2 will continue execution up till 14 seconds from 9 seconds. So now 23 units milliseconds of time have been are over. Okay, so now only P3 is left. So then P3 will continue execution up till 44 milliseconds. So up till then all the processes have completed their execution of IO also. Only P3 is left to be executed in the input output operations, left to be doing input output operations. So that will continue for 3 more milliseconds up till 47. So up till 47 no more processes are there to be scheduled in the CPU. Okay, so this is the sequence of completion of the processes, of course. That is, P1 will be completed, will complete its execution first, followed by P2 and then P3. So I have just demarcated this here to signify that there are IO processes that are happening in the background. Okay, so is this clear enough? I know this is a comparatively harder problem compared to the straightforward problems that we were solving up till now. So is this clear enough? Do you have any doubts? If anyone has any doubt, we can move ahead. Any feedback? Is this clearer now, what I was meaning by non-preemptive? Yeah, this is the Gantt chart. This is the Gantt chart. and I have actually used tables for creating the Gantt chart. Okay. So do you have an idea of the question? Like, do I repeat the question? Okay. So let's get back to the question once again. Okay. So yeah, if you have an idea of the question, so we need to schedule the processes in the CPU considering their CPU burst times, the CPU burst times that are required for the processes, right? So but at first all the processes need some IO time. Okay, so for what unit of time will it be doing, will the processes be doing IO only? That is 20% of the time, 20% of the total burst time. Okay, so what happens? Let's move one by one into the Gantt chart. At the 0th millisecond, so the short term scheduler will try to pick up P1 since it has the shortest CPU burst. So at the 0th millisecond, P1, P2 and P3 all are there in the ready queue. Okay, so it will pick up the shortest process which requires the shortest CPU burst, that is P1. Okay, so what happens is that it moves to the running state and then it immediately requires IO. So it will be removed from the running state. Then the short term scheduler looks at the two leftover processes and the shorter process among them is picked up, that is P2. The picture stays the same with P2 also, that also requires IO at first. So it will go from straight away from the running state to waiting state again. Okay, waiting for IO to be over. Only P3 is now left. So the same thing happens with P3 also, that is it also requires IO operations at first. So it will also go from running state to the ready state. No other processes are left in the ready queue to be scheduled into the CPU. So this happens for the first 2 milliseconds. After the second millisecond, what happens is that P1 has returned from IO and is currently present in the ready queue as the only process that can be scheduled, that can be given some CPU time. Okay, so the short term scheduler picks up the only process that is left in the CPU. Doesn't matter how much CPU burst time it requires, it may have required huge CPU burst time, it doesn't matter, it is the only process that is currently present in the ready queue. Okay, so after 2 milliseconds P1 is picked up. What happens after 4 milliseconds is that P2 has completed its IO burst and is present in the ready queue now. Yeah, this is the complete solution. If you want a more descriptive solution, I will re-prepare the slides and update them afterwards, and maybe give you some links also where you can get help. Okay, so yeah, I just wanted yeah, so anyway, let's move on to the description then. So what happens is that after 4 milliseconds P2 is currently there in the ready queue, but P1 continues executing in the running state. After 6 milliseconds P3 also appears in the ready queue, but P1 is still executing. It is a non-preemptive process and non-preemptive algorithm, and the process that is already there in the running state stays in the running state until it completes execution. So that happens after 9 milliseconds, that is after the process P1 has completed its own CPU burst. So after 9 milliseconds P1 goes into IO because it requires IO. The CPU is free now, so the short term scheduler picks up the next shorter process comparing the CPU bursts. So it picks up the next shorter process from among the ready queue, which is among P2 and P3. So P2 is the shorter process comparing the CPU burst. So then P2 is picked up at 9 milliseconds. So after 1 millisecond, at the 10th millisecond, what happens? What event happens is that P1 has completed its IO burst also, and P1 has completely completed all the burst time, and it has completed execution. So P1 is now done at 10 milliseconds. Okay. So up till 23 milliseconds, that is up till completion of CPU burst of P2, no other event occurs in the background. P3 is only there in the ready queue sitting, and P2 is running up till completion. So then after 23 milliseconds is that P2 requires, what happens is that P2 requires 2 more milliseconds to do IO. So by that time it has transitioned from the running state to the waiting state for IO. P3 can be given the CPU time, because that is the only process that is there in the ready queue still. So now next P3 is picked up by the short term scheduler at 23 millisecond mark. Okay, so what happens after 25 milliseconds is that P2 has completed its 2 seconds of IO burst, and it has also completely completed its execution. So no other process is there in the ready queue, only P3 is there, and P3 moves up till completion, that is it requires 21 burst cycles up till completion, 21 milliseconds up till completion. So what happens after 44 milliseconds on the clock is that P3 moves on to IO for 3 more milliseconds. Okay, and then it finally completes its execution. So execution order is P1, then P2, completion order is P1. P1 actually completes here. So this is the Gantt chart. The Gantt chart actually shows which processes are there in the running state. It does not show which process has completed. Does 2 at first is arbitrary? No, these are actually signifying the times. So these are the time points of the Gantt chart. This is the Gantt chart. Okay. So this 2 means that this is the time quantum 2. Okay. So this is the point 2. Okay. This is the point 4. This is the point 6. Like this is the 6 millisecond mark. This is the 9 millisecond mark. That is what is signified by this 9, 10, 23. Okay. That might have confused you. Anyway. So yeah, that is okay. Anyone else has any questions? No, no, it does not take that. See, I have signified these 2, 4 and 6 because it signifies an important event in the background, not just what is happening in the CPU. So at 2 millisecond mark, what happens is that P1 has completed its IO burst. At 4 millisecond mark, what happens is P2 has completed its IO burst. At 6 millisecond mark, P3 has completed its IO burst. That is why I have signified those times, even though nothing is happening. Please give me 1 second. Hello, I hope I am audible still. Okay. So what happens at 6 millisecond? What happens in 6 millisecond mark is that P3 has completed its IO burst. Okay. So these are the things that happen. So that is why I have signified all these times. At 9 millisecond mark, finally you are seeing that there is a context switch from P1 to P2. That is, P1 has completed its running time. It has gone into IO, and the CPU can be scheduled to P2. So that is what is happening. That is why I have marked all these times. So these are not arbitrary. Okay. So what happens after 10 millisecond mark is that P1 has completed its execution. Okay. So I hope that is clearer now. Okay. Any other doubt you have? Anyway, let's move to the another question. So now, can you give me an estimation of what percentage of the time does the CPU remain idle, given this Gantt chart that is of the previous problem only? What percentage of the CPU time does it remain idle? So since it's already time, I'll just quickly go to the answer. It will be in these 2 milliseconds it will stay idle, in these 3 milliseconds it will stay idle. So total of 5 milliseconds among 47 milliseconds it will stay idle. So if you calculate the percentage, it is 10.64. Okay, anyway, there are 3 more questions related to synchronization, but these are pretty straightforward. Okay, am I audible? I guess I am audible. Okay, anyway, so there are 3 more questions that are related to synchronization that are pretty straightforward. So yeah, I'll be uploading those. If you have any doubt, you may ask me. Anyway, thanks for joining the session. Sorry for the interruption in between. Actually, my electricity has gone off, so yeah, there is an unstable internet connection. Anyway, we are done with the session. So thanks for joining. Thank you so much for joining. Yeah, I hope I'm audible towards the ending part. So yeah, thank you for joining. Meet you in the next session. Thank you. You can drop off from the call.